Hi, I am Satvik Patnaik, part of the group covering the paper Two-photon induced coherence without induced emission, and this is our presentation as part of the course project for PH 530. So this is the outline of our presentation. I'll be covering the first two sections, which covers the background and the motivation of the paper as well as the theoretical framework. So let's start with the background. What is induced coherence without induced emission? Now let's start with the classical optical coherence that is observed. For this, we require stimulated emission or induced emission, which is done by injecting light into a crystal, which triggers more photons at the same phase. And the increase in the photon count as we increase the light pump is the signal for the classical optical coherence. This is used in lasers, for optical amplifiers, LiDAR, as well as other communication systems. And the phase coherence is signified by the count rate increase, and this is inseparable classically. Now, in the quantum domain, what happens is that the coherence can arise with zero induced emission. It's a purely quantum mechanical effect which is caused due to the indistinguishability of probability amplitudes, and it is observed in the first order intensity, unlike other quantum phenomena in quantum optics, which require second order intensity. Now, the phase on the undetected, what happens here is that the phase on the undetected photon shows up when we detect the detected photon, and this enables sensing at inaccessible wavelengths that we will explain in more detail later. Let's start by talking about single photon induced coherence. So the core mechanism is the SPDC in the first nonlinear crystal. It produces a signal and an idler photon, and then the uh, same pump is then used for SPDC in a second nonlinear crystal. Now, what happens now here is we have two pairs of photons, a signal and an idler. When both the idler photons are overlapped, the I1 is spatially overlapped with I2. What happens is that the modes become indistinguishable, the idler modes, and then there is no way to tell. And when we detect the signal photon, there is no way to tell which crystal the signal photon actually came from, and then this leads to uh, first order interference in the signal, gives a signal interference pattern, and which leads to the observed induced coherence. The signals When we observe the signal photon, single photon level, the signal counts are roughly proportional to 1 plus minus v times cos times the phase that is accumulated in the idler, and that in the undetected, which we do not detect. The phi I is the undetected idler photon phase. Now, the limitation here is that it is still a single photon effect. The phase sensitivity is still it is the Heisenberg limit at 1 by n, which is the quantum enhanced sensing, but then at a single photon level, this is still the same as the classical short noise limit that goes as 1 by root n. And so we cannot achieve Heisenberg limited precision with just single photons, and that is the hallmark of quantum enhanced sensing, which is missing. So the big idea of the paper is to extend this to two photons, multiple photon regime, which actually then leads to the quantum enhanced sensitivity pause showing up due to the 1 by n differing from 1 by root n sensitivity. So the phase shifted photon, which is the idler photon, never reaches the detector, and we detect the signal photons at the detectable optical frequency, which carry the doubled phase information. Here in the expression, we can see the general n photon state with the accumulated phase factor of the idler in one term. Now, for n equal to 2, the phase phi I on the undetected idler actually shows up as a 2 phi I modulation in the detected signal photon, which is helpful in improving the sensitivity. Now, let's move on to the main theoretical framework, which is the two-photon quantum state. As we saw in the previous slide, the two-photon state has actually three terms. One which has a double phi factor, and it's basically this is the term which signifies both pairs coming from the first nonlinear crystal. There's a second term without any phase factor, and that signifies both pairs coming from the second nonlinear crystal. And there's a third term which is the cross term, and which signifies one pair from each crystal. And we are interested in only the first term, which actually carries the 2 phi I phase factor, and this is what leads to the quantum enhanced sensitivity. The second term has no idler phase factor, and it's just a reference amplitude. The third term is now is it carries, as we can see, it carries only a single the single phi I phase factor, not 2 phi I, and thus it contaminates our 2 phi measurement, and therefore it must be eliminated. And this is done by the Hongo-Mandel interference at the beam splitter, which filters out this third term, which is because when one pair comes from each crystal at the beam splitter, they constructively interfere to give two photons to a single pair coming out from one output of the beam splitter, and this leads to only pure 2 phi I signal in the coincidence measurement when we measure uh, a coincidence measurement for both the detectors at the same time. Due to the Hongo-Mandel effect, the third term doesn't lead to a coincidence at both the detectors. Yeah, this is the key physics here, the Hongo-Mandel interference. So when two identical single photons enter the 50-50 beam splitter from opposite ports, what happens is the quantum interference forces both the photons to exit out through only the same port. So when we do a coincidence detection at both the detectors at the output ports, we don't get a coincidence due to the Hongo-Mandel effect when there are single photons coming from each of the input ports. This is the quantum mechanical photon bunching effect basically. And this filters out the term 3 because the term 3 has one signal photon in S1 and one in S2, identical photons from each crystal. This S1, S2 are the signal modes, and these, when they overlap at the beam splitter, and they undergo the Hongo-Mandel interference, and they always exit to the same port, and thus never lead to coincidence between D1 and D2. Only the first and second term survive here, and thus we are able to retrieve the 2 phi I phase interference pattern, and thus we can extract the 2 phi I factor out. And here we can see that the coincidence detection probability is 2 plus 2 cos time 2 phi I, which is again an improvement over the single photon coherence, induced coherence due from phi I to 2.
Hi, I am Kshitij. So far, we have been working with the idealized picture with the monochromatic photons and a single frequency. But real photons from a femtosecond laser have a spectrum. So the simple equation 2 we derived, that was P is equal to 2 plus 2 cos 2 phi I needs to be generalized to account for this. This is exactly what equation 6 of the paper does. It is a double integral over all possible ideal frequency pairs omega I and omega I prime. The joint spectral amplitude f omega s f omega I tells you the probability amplitude for generating a single photon at omega s paired with an idler at omega I. We square it because we are dealing with two photon pairs, and inside, instead of a single cosine, you get cosine of omega I plus omega I prime. The phase picked up by each idler frequency independently as the mirror moves. Now, in the notebook, we assume that the joint spectral amplitude is separable, meaning that the signal and idler frequency are independently distributed. This is valid here because we are putting a narrow 2 nanometer interference filter on a single photon before detection, which effectively factorizes the joint spectrum under that assumption. And using a Gaussian Adler spectrum of with sigma, the entire double integral collapse into a beautifully closed form, which is denoted here. This equation, which is uh, Px is proportional to 2 plus 2 exponential of minus 2 sigma square x square by c square, and cosine of 4 omega I naught x by c. So this equation has a Gaussian envelope that decays as you move the mirror away from the balanced position, multiplied by a rapidly oscillating cosine. The cosine has exactly double the frequency compared to the single photon case, confirming the 2 phi I modulation. The Gaussian envelope tells you the coherence length of over the two photon interference remain visible. Now let's just make sure that all numbers are consistent. Energy conservation in SPDC requires 1 over lambda pump. 1 over lambda pump is equal to 1 over lambda signal plus 1 over lambda idler. On putting lambda pump to be 390 and nanometer and lambda signal to be 632.8 nanometers, we get lambda idler to be 1016.4 nanometers. Then our notebook confirm this. This matches with the experimental value within 0.1%. Now the bandwidth parameter matter because they determine the coherence envelope we'll see in figure 4. The pump has 1.84 uh, nanometer full width half maxima, bandwidth at 390 nanometers, and the signal filter is 2 nanometer full width half maxima at 632.8 nanometer. When you combine these under in energy conservation, since the idler frequency is constrained to be the pump minus signal, you get an effective idler spectral width of sigma effective. The naive estimate gives a coherence envelope full width at half maxima of about 96 microns. But the paper's figure 4a shows an envelope of roughly 40 microns. The discrepancy comes from the phase magic bandwidth of the 1 millimeter BBO crystal, which the simple two filter model does not capture. So in the notebook, we adjust sigma to match the observed 40 micron envelope, and that's what we use in all subsequent simulations. Uh, the two the two fringe table in the table are worth highlighting. The single photon fringe period is lambda idler over 2, which is 508 nanometer of mirror displacement, and the two photon fringe period is lambda idler over 4, which is 254 nanometer. The halving is the direct experimental signature of the two photon induced coherence. Moving on, our figure 3 is the central experimental result of the paper, and we reproduce all the three panels. First one is panel A. Panel A is the D1 single count rate. As you scan the idler mirror, you see a sinusoidal fringe with 51.7% visibility and period of 1016.4 nanometer, which is the idler wavelength. This is the standard single photon induced coherence. Panel B is the D2 single count rate. It is the complementary output of the beam splitter. So it's anti-correlated with D1. That is when D1 goes up, D2 goes down. The same period, same visibility of the 47.8%, just shifted pi in the phase. And panel C is where new physics is. And panel C is just something new. The coincidence count rate between D1 and D2 shows a fringe with period 508.2 nanometer, exactly half the single photon period. The halving is the 2 phi I modulation, and the visibility is 22% lower than the single photon case due to the imperfect idler mode overlap. The mean count rate is also dramatically lower, about 16 hertz versus 60,000 hertz for single counts, because coincidences require the simulation generation of two photon pairs, which is a much rare event. Now let me explain the simulation methods and our key observations. The simulation is kind of straightforward but carefully parameterized. We define the mirror displacement x running from the range 0 to 1.1 microns. The round trip phase is phi I is equal to 2 ki times x, where ki is the idler wave vector. For the photon counts, uh, D1 follows 1 plus V1 times cos phi I, and D2 follows 1 minus V2 times cos phi I. These are complementary as we expected. For the coincidence, it's 1 plus V12 times cos 2 phi I, and that is the argument cos phi I is double. In this case, it has become 2 phi I. We also add realistic Gaussian short noise of about 3000 hertz standard deviation for the single counts and 5 hertz for the coincidences. And we subsample 150 scattered points from the continuous curve, which mimics the discrete experimental data in the paper. The smooth line on the top of the scatter is a sinusoidal fit, just like the paper show, and we will see the figure next. The key result to take away, uh, the panel C's fringe period is exactly half of the panels A and B, and we verified this analytically. Single photon period is lambda I over 2, which is equal to 508.2 nanometers. two-photon period is lambda I over 4, which equals 254.1 nanometer. This factor of 2 comes directly from the cos 2 phi I in the coincidence probability, which itself comes from the ongoing. This factor of 2 directly comes from the cos 2 phi I in the coincidence probability, which itself comes from the HOM interference, filtering out the cross term. All right, this is the figure 3 of the paper that we reproduced. Uh, as we scan the idler position from 0 to 1.1 micron, the counted at detector D1 oscillates sinusoidally, as we can see here, and the mean is around 60,000 hertz, and you can see it swing from nearly 0 to up to 95,000 hertz. Now, as the first thing that we can appreciate here, the modulation period is 1016.4 nanometers. That's the wavelength of the idler photon. But D1 is registering 632.8 nanometer signals photon. The detector has no idea the idler even exists. Yet the phase applied to the undetected infrared photon is showing up perfectly in the visible photon counting. That is the Zhou-Wang-Mandel effect, induced coherence without induced emission. The middle panel of shows D2, the other output port of the beam splitter. Notice two things. First, the period is identical, still 1016.4 nanometer as it must be, since it's the same idler phase driving the modulation. Second, this is important that D1 and D2 are exactly out of phase with each other. You can see this. Uh, when D1 is maximum, and D2 is at the minimum, and vice versa. This energy conversion at the beam splitter. A photon that don't go to D1 goes to D2, and the visibility here is 47.8%, slightly lower than D1, which is consistent with small asymmetries in the optical alignment. So yeah, panel 1 and B together confirm the standard single photon induced coherence. Nothing new yet. This is a known uh, Zhao. So panel 1 and B confirms standard single photon induced coherence. Nothing new yet. This is a standard Zhou-Wang model. Now, look at the bottom panel carefully and compare the x-axis scale with the panel above. The coincidence count rate that simultaneous clicks at both D1 and D2 also oscillate sinusoidally, but count the number of oscillation across the same 1.1 micron range. In panel A and B, you see roughly two full cycles. In panel C, we can see almost double, like four cycles. The fringe period has been cut in half from 1016.4 nanometer down to 508.2 nanometer. That is the 2 phi I modulation. The same physical mirror displacement now produces twice the phase oscillation in the coincidence signal. That is the hallmark of quantum enhanced phase sensitivity. We have doubled our phase resolution without changing anything about the probe. Also, we can notice that with the mean coincidence rate is only about 60 hertz as compared to the 60,000 hertz for the single counts. That's a factor of 1,000 lower, and it makes physical sense. And a coincidence even requires two photon pairs to be generated simultaneously, which is a much rarer process than the generating a single pair. And in this case, the visibility is 20%, which is lower than the 50% in the single photon panels. The paper attributes this to the imperfect spatial overlap between the two island modes I1 and I2. The small differences in beam divergence, spatial mode shape, and mirror reflectivity all degrades the mode matching and wash out the.
Hello everyone, I am Sachin and I will be explaining from slide number 14. So as you have established so far, the quantum interference relies on indistinguishability. But what happens when we move the idler mirror away from its perfectly balanced position? So as the mirror is displaced, we introduce the time delay between generation of first idler photon and second idler photon. So this time delay introduces temporal distinguishability, which means now the universe can tell which crystal the photon pair comes from, causing our two-photon visibility to drop. So how they have done it is they have an experimental setup. So we took measurements at specific mirror position, which are minus 35, minus 15, 0, 15, and 35 micrometers. So at each of these positions, we record the minimum maximum coherence to determine the fringe angle. So here is the code for that. So yeah, I'll explain everything that's in this code. So firstly, while the blue dots represent the minimums, the red dot represents the peak coincident counts, with the error bar indicating our standard deviation. When you apply a Gaussian fit to these plots, we see a clear coherence envelope. The peak visibility is at approximately 22% right at the balanced position x equals to 0, and it steadily decays as absolute value of x increases. So this perfectly illustrates that the photon must develop perfectly in time to maintain their quantum indistinguishability. Okay, so now this was the experimental envelope. So now what we are going to do is do the numerical simulation of it. So now we transition from experimental data to fully numerical simulation of this phenomena. So now in the panel B, you have to reproduce this. What we utilize is the full multimodal analytical derivation, which is given in equation number 6 from the paper. So what this equation does is it represents the exponential decay term and the rapid cosine oscillations in a single, which represents the actual quantum interference fringes. So what this is the probability function Px is proportional to 2 plus 2 e to the power minus 2 sigma x square by c square, and it's multiplied with cos for omega I naught x by c. So this formula is fascinating because it has both the terms, the exponential decay term as well as the rapid cosine oscillation. Yeah. So how we are going to define by what we do, we adjust our effective idler spectrum with different sigma factor, and we try to match the 40 micrometer scale, which is full width half maxima observed in the experiment. If you direct attention to this, yeah. If you direct your attention to this insert graph, we have zoomed on the absolute center. Now you can see we have a tiny window of 0.45 micrometers. You can clearly resolve the individual interference fringes. Now that the fringes displacement period is approximately 254 nanometers, which is exactly lambda idler by 4. So because the standard single photon period is lambda by 2, roughly 508 nanometers, this halved to 254 nanometers previously visualized confirmed that we have observed a double phase modulation. So what we have is we have a double phase modulation because of the signature of our two photons. Okay. So yeah. Now moving on to how we derive of an analytical solution. So yeah. I'm not going to go in too much of a detail, but here are the steps. So what we do is we begin by assuming Gaussian profile for the marginal idler spectrum amplitude. After that, what we do, we integrate out the single photon. And in the next step, what we do, we take the Fourier integral of the spectrum to translate it from frequency domain into spatial displacement domain, yielding a function IS. Yeah, that contain both the rapid oscillations and the Gaussian decay, as you can see from this equation in step 2. In step 3, what we do is we took this double integral from a multimodal theory, and through manipulation, what we do is we find that this complex integral nearly fits into real part of Ix squared. So yeah, that was an interesting term, this directly fits into the real part of Ix squared. So finally, in step 4, the squaring the integral gives a final analytical result, which is e to the power I4 omega I naught x by c. So for double the frequency oscillation, we are gonna multiply it by we are gonna multiply it by e to the power minus 2 sigma square x square by c square for our annual part. So this is a very thought-provoking result. Okay. So now moving on to the next slide, what we have in the slide is bandwidth estimation and envelope width. So what we observed is the theory and experiment don't always perfectly align on this trial. We initially calculated the effective bandwidth using only the known parameters of the laser and filters. We encountered a discrepancy. The 390 MF laser has a certain bandwidth and our 332.8 nanometer signal interference filter has a 2 nanometer bandwidth. So if we sum these in quadratures, we get a theoretical sigma effective of about 1.87 into 10 to the power 12 reading per second. Plugging this into an envelope formula predicts a rather wide envelope with a full width at half maxima, roughly 96 micrometers. So, but as I have already shown in the slide, it is roughly 40 micrometer from the experimental results. So why is this difference? So this naive calculation, which we did is overestimates the coherence length because it ignores the phase matching bandwidth constraint of the 1 mm BBO crystal itself. So it doesn't, in a sense, it ignores the phase matching bandwidth constraint of the 1 millimeter BBO crystal itself. So what it does is it then just further restricts the actual spectrum of the idler photons to accurately simulate the experimental reality. We have to adjust our sigma to 3.1 into 10 to the power 13 radians. That actually perfectly matches with 40 micrometer envelope and shown how physical crystal produce our quantum states. Okay, so this is all in the slide. Yeah. Now what we are going to do, we are going to try to reproduce our figure 5 from the paper. So absence of induced emission, we are going to try to do this. So this is arguably the most critical conceptual hurdle of this paper. So how to prove the absence of induced emission? In classical optics, if you inject light into a gain medium to create a coherence, you trigger stimulated or induced emissions. Yes, this is true. This means the injected photons cause more photons to be created at the exact same phase, and you have a massive spike in your photon count rate. Yeah, so to prove our efficiency is purely quantum, what we do, the authors have described a brilliant method. They place a detector directly in the S2 signal mode before the beam splitter. So the experiment starts with the first idler mode, physically blow, and they monitor the signal. Then count the rate. Then at 200 second mark, they unblock the I1 and inject it into second crystal. If classical stimulated emission were responsible for our coherence, unblocking I1 must cause a sudden increase in S2 count rate. The entire validity of induced coherence without induced emissions hinges on this result of this specific test. Okay. Okay, so now I'm going to show what is the result of this test. So this test is this gives us a very critical test analog with our simulation. As you can see, when the barrier is removed at time t equal to 200 seconds, absolutely nothing changes. Yeah. As you can see, absolutely nothing changes. The single count rate remains flat at approximately 80,000 hertz, and the constant rate remains flat at roughly 80 hertz. So this, what this physically interprets is, it has profound interpretation. So the phase coherence we are measuring is not due to stimulated emissions or additional photons. No energy is being transferred, and no new photons are being born because of this injected light. So what actually is happening instead, the coherence arises purely from quantum indistinguishability, because there is no way to know whether a detected photon pair originated from the first pass through the crystal NL1 or the second passed through the crystal NL2. The probability amplitudes superimpose and interfere. So this flatline graph is the definitive proof that we are observing a generally known classical multi-photon quantum mechanical effect. So yeah.
Hello everyone, I am Abhimanyu and I will be presiding over the rest of the presentation. And so, alright, let's begin. And as you can see in this slide, so essentially what this slide does is it gets the central claim of the entire paper. And it's really just one comparison of what happens to a single photon versus what happens when you have two. So on the left, you can clearly see when you have the single photon case, the intensity goes from V times cosine of phi, and so essentially for one full oscillation cycle, for every 2 pi change in the idler phase, the phase sensitivity here scales as 1 over root n. So that's the standard short noise limit. It's the same limit you hit with any classical measurement strategy. Nothing quantum enhanced about it. So the mirror displacement period in this case is lambda idler over 2, which works out to be 508 nanometers, as you clearly see. So let's take a look on the right side. So as you can see, the coincidence count goes as 2 plus 2 cosine of 2 phi. So which is essentially the same physical phase phi being applied to the same undetected idler photon, but the detected signal oscillates twice as fast. So 2 full cycles per 2 pi. The period in mirror displacement is lambda idler over 4, which comes out to be 254 nanometers. So the factor of 2 in essentially the factor of 2 is the entire point. Phase sensitivity now scale over as n, the Heisenberg limit, as 1 over n, which is essentially the Heisenberg limit. And the fundamental quantum advantage, which is essentially the fundamental quantum advantage. And it's happening here while the probe photon, the one actually picking up the phase, is never detected at all. So as you can also see in the footer of the slide, that the same physical phase by twice the oscillation frequencies in coincidence count. So that's actually the quantum enhanced sensing with the undetected photons. So yeah, so this is what actually looks like when you plot it. So on the left, the single in the blue graph, the single photon fringe smooth one cycle across the full range of 5, clean and classical. On the right side, the red one, the 2 photon coincidence fringe, same x-axis range, but you can immediately count that there are twice as many oscillations backed into the same interval. The fringe is compressed. The period is half. This plot is something we add ourselves. It doesn't appear as a standalone figure in the paper. We put it in because we felt the direct visual comparison makes the quantum advantage more immediately obvious than any of the experimental data plots that we have. So when you look at figures 3 and 3C in the paper side by side, the period difference in there, the period difference is there, but you have to look carefully because the axis in mirror displacement, the axes are in the mirror displacement, not in phase. Here it's unambiguous. One curve oscillates twice as fast as the other. That's the whole story right there. So yeah, this is what we reproduced. So for figure 3, as you can see, the interference fringes, we match the visibilities of 51.7% at D1 and 47.8% at D2 and 22% in the coincidence channel. So, so we implemented the correct phase relationship, cosine 2kix for the single photon panels, cosine 4kix for the coincidence, and verified both fringe periods and analytically. The rate difference between single photon counts at around 60,000 hertz and coincidence count at around 60 hertz comes naturally from the 2-pair generation probability scaling as the square of the single pair rate. For figure 4, the coherence envelope, we implemented the full multi-mode formula, equation 6, and reproduced the Gaussian fall-off. We also derived analytically why the envelope has to be Gaussian, and we identified why the native bandwidth estimate of 96 microns doesn't match the 40 micron full width half modulation. The phase matching bandwidth of the BBO crystal is the additional constant the simple calculation misses. And for the fifth figure, the absence of induced emission, we simulated the flat count rate experiment, confirmed no change at the unblocking event, and explained why the result rules out of stimulated emission as the origin of coherence. And then we add the phase sensitivity comparison plot on the previous 2 slides, not in the paper, but a useful pedagogical addition makes the quantum advantage visibly explicit. So now the next slide. So essentially generalization of n photon induced coherence. So this paper demonstrates n equals 2, but the result sits inside a completely general framework, and it's worth understanding where this is going. So the general n photon state has the form 1 over root 2 e to the power I n phi I times the n in S1, ket n in I1, plus ket in S2, ket N2 in I2. When you work through the coincidence probability, you get P equals 2 plus cosine of n times phi. The phase modulation scales linearly with n. So the 4 cases on this slide tells the story cleanly. So n equals 1 is the original Zhou-Wang-Mandel effect from 1991, phase sensitivity 1 over root n short noise standard quantum limit. And n equals to 2 is this paper, the phase sensitivity over phase sensitivity 1 over 2. Coincidence fringes at twice the frequency. Heisenberg limit reached for the first time in the undetected photon framework. So n equals to 3 and n equals to 4 are future work. 1 over 3, 1 over 4, the fringe period keeps halving. So the sensitivity keeps improving. The key challenge for getting to higher n on this source side, the key challenge for getting to higher n is on the source side, and so that's that. And generating a high purity 2-photon Fock state from SPDC is already non-trivial. The frequency anti-correlation had to be removed with interference filters in this experiment. For n equals to 3 or 4, you need brighter sources, better spectral engineering, and photon number resolving detectors. But the theoretical framework is already there. The undetected photon approach is especially attractive at high n because the probe photon, the one doing the sensing, can be at any wavelength, mid IR, terahertz, whatever the application demands. The detection always stays in the visible. That's the real power of this scheme. So now let's go on to the next slide. So yeah, so now let's go on to the application. So why does it all really matter? The core structural advantage of the whole scheme is that the photon doing the sensing and the photon you detect are different wavelengths. The idler probes the sample, the signal carries the information back to your detectors. That decoupling is the engine behind everything on this side. So first is the mid-IR quantum imaging. Molecules have strong vibrational absorption features between 3 and 12 micrometers. This is called the molecular fingerprint region. If you want to identify a compound or image a biological sample at high contrast, this is the wavelength range you care about. The problem is that mid-IR detectors are expensive and need cryogenic cooling. The induced coherence scheme puts the idler in the mid-IR where it interacts with the sample and keeps the signal in the visible where you read it out with a cheap silicon detector at room temperature. This paper now adds the Heisenberg limited phase sensitivity on top of that, better signal to noise at the same dose or to the same sensitivity at lower photon exposure. Now, then comes quantum spectroscopy. If you put in an absorbing sample in the idler path, the visibility of the single fringe drops in proportion to the absorption. You get a full infrared absorption spectrum without even detecting an infrared photon. With 2-photon coherence, the signal to noise ratio improves towards the Heisenberg limit, relevant when you are trying to detect trace concentrations or weak absorbers. Quantum OCT and polarimetry. So it's essentially optical coherence tomography is already in clinical use for retinal imaging. The undetected photon versions use infrared and reduced tissue scattering while reading depth information from the visible signal fringe. 2-photon coherence improves the phase sensitivity of each depth slice. Quantum polarimetry extends this to bifringent samples. Next, there is quantum metrology and n photons extension. The Heisenberg limit is the fundamental bound on phase estimation. Reaching it with undetected probe photons is conceptually new, and the probe wavelength is now completely decoupled from the detection wavelength. And as n grows beyond 2, the sensitivity keeps on improving. So the core message is simple. This paper turns a fundamental physics demonstration into the foundation of a practical sensing technology roadmap. So now let's move on to the summary and conclusion part. So the paper for the first time demonstrated two-photon induced coherence without induced emission. That's genuinely a new thing. The Zhou-Wang-Mondale effect has existed since 1991 and has been a single photon only the entire time. And this paper takes it to the multi-photon regime, and in doing so achieves quantum enhanced phase sensitivity in the undetected photon framework for the first time. So the signature is unambiguous. Phase shift phi on the undetected 1016 nanometer idler produces a 2-phi modulation in the detected 632 nanometer signal. The coincidence fringe period halves from 508 to 254, and they confirm the without induced emission part rigorously. Unblocking the idler produces no change in the single photon count rate, and the coherence is purely from quantum indistinguishability. What essentially we have produced was all three experimental figures: interference ranges, coherence envelope, and the induced emission control, plus a phase comparison plot we added ourselves. We matched the key numbers, visibilities of 51.7, 47.8, 22%, and the half fringe period in coincidence, the Gaussian envelope with 40 micron full width half wave modulation, and the flat count rate that rules out stimulated emission. The key insight in one sentence is that HOM interference at the beam splitter kills the contaminating single phi term, leaving only the two photon terms. And the resulting coincident fringe oscillates at twice the frequency. Everything else follows from that. Future directions that people can work on is higher end for steeper Heisenberg scaling, chip integrated non-linear interferometers for deployable sensing, and application specific demonstration where the quantum advantage is measured explicitly against the short noise baseline. This paper is proof of principle. The physics is established, and what comes next is making it useful. So thank you for watching.